Okay, good afternoon, everyone. Welcome to today's online session. Today will be session 3, Design Solutions for Projects that require 3D Modeling and Analysis. Okay, so just make sure that you get our permission before you start sharing these materials with anyone else. You can share this material with engineers within your office. Just for lecture purposes, just make sure you receive our permission beforehand. Okay, so before I begin, I'd just like to go over a couple of learning objectives. So at the end of this course, we would like all participants to be able to understand, first and foremost, the fundamental concepts of 3D numerical analysis. So essentially, why you need 3D modeling and when it would be useful for you. And then benefits of 3D analysis, so unique and special benefits of performing your modeling in 3D. Then also geotechnical project conditions that necessitate 3D analysis. So there are certain types of projects that specifically benefit from 3D analysis. So we'll be going over those types of projects so that in the future you'll be able to recognize what type of projects would best be modeled in 3D. Okay, and here's just an index or an overview of how the session will be divided into. So first we'll have the background. We'll talk about how to decide dimensions of analysis, types of dimensions in the analysis, and then why we use 3D analysis, so specific reasons that 3D analysis is used for particular projects. And next, how to use 3D analysis. So we'll discuss the steps that are needed in order to generate an accurate and an efficient 3D model. And then last, we'll be going over case studies, so certain projects that were modeled in 3D and how and sort of the results and how it was used effectively. Okay, so Chapter 1, how to decide the dimensions of the analysis and then types of dimensions in the analysis. So we'll be going over several types of model types, and we'll sort of go over how to decide whether or not to use 2D or 3D analysis or 3D modeling. Okay, first, analysis can represent the results of the project site. So as you can see, if you look to the left here, what we have is a project that's symmetric along the y-axis or in the longitudinal direction. So as you can see, because of this project geometry, what we can do is we can just generate a very simple 2D model, and then we can just extrude those results along the y-axis. So essentially, just assuming that aside from project geometry, that loading conditions are the same. Then what we can do is we can just create a simple 2D model. So instead of having to create a sort of larger, more complex 3D model, we can simplify this into 2D. So this is something that engineers do quite often, just to make the analysis and the modeling more efficient. Now, if you look to the right here, as you can see, this project site, this is a tunnel with a connecting gallery. This project is not symmetrical in the longitudinal direction. So as you can see, for the cross-section A and the cross-section at B would be very different. So in this case, you wouldn't be able to create one 2D model and extrude it. What you could do is you could create 3 separate 2D models, or you could just simply create a 3D model to represent the entire project. But just keep in mind that project geometry such as this typically requires a 3D type of analysis. So that's an important thing to keep in mind, is that whenever geometry is symmetric, you're sort of better prepared or better equipped for a 2D analysis as opposed to a 3D analysis. Now let's talk about plane strain conditions. So as you can see, this is a slope stability type project, and although the geometry isn't quite fully symmetric in the y direction, in the longitudinal direction, if the strain itself is negligible, in other words, if the strain acting in the y direction is negligible, then we may be able to model this project in 2D as well. And then also for retaining wall projects such as this. So for example, what you can do is you can take a project such as this, where the geometry is not perfectly symmetric, but you can still create a perfectly sort of symmetric 2D model and just assume symmetry. This is just dependent on the fact that conditions or that strains in the y direction and the longitudinal direction are negligible. So it's really up to the engineer, or up to you to decide whether or not 2D analysis would be sort of beneficial in this type of project. So it really depends on your project, what your clients want, sort of the scope, the budget, etc. But just keep in mind that even though the geometry isn't perfectly symmetric, 2D analysis may be an option, just as long as certain factors are fulfilled. Okay, and then more examples of plane strain conditions. So another tunnel. So once again, the tunnel isn't perfectly symmetric, but just for example, the sake of simplicity, you may be able to create a 2D model. And the same behavior or the same principle applies to these bridge abutment type projects. So just keep in mind that whenever project geometry is symmetrical, just in the longitudinal direction or close to symmetrical, 2D analysis is especially useful to help you save time and effort. And then let's go over some other symmetry conditions. So as you can see, this is an embankment type project where it's symmetric, just going along this axis here. So what you can do, instead of having to create the entire model in 2D, what you can do is you can create half of the model and then assume, or then just extrude or extrapolate the forces or the reactions on the other side. So just once again, keep in mind that the forces have to be symmetrical as well, in addition to the geometry. So this is another sort of tip or sort of method that can save you time in the long run. If you have a perfectly symmetric model, you can just create half of that model and then sort of extrude or extrapolate the other displacements and strains and reactions just based on what you get with this model or with a half model. Okay, and then we also have axis symmetric conditions. So here's an example where the project is symmetrical in the rotational direction. So what you can do is you can just take sort of this cross-section here, perform your analysis, get your results, and then just sort of extrude it rotationally. So in other words, if you just get your results or your calculations just along this plane here, you'll be able to extrapolate your results and your displacements, etc. for the entire 3D structure. So this is a tunnel, or I believe a pile in soil. So what you can do is you can, if you have a single pile project, what you can do is you can just take, and that's, fully symmetric in the rotational direction, you can just create a model similar to this and then just, extrude your results rotationally. So that's another sort of method that could save you a lot of time in the long run. So just keep in mind that the whole purpose of modeling in 2D is just to simplify the modeling process and the analysis process and to save you time and to help you work more efficiently. Okay, so now here's some examples of some projects that are better modeled in 3D. So as you can see, this is a tunnel connecting gallery project. So you have a main tunnel with 2 connecting galleries. So you also have a station, I believe, and also some other objects or some elements acting in the Y direction. But as you can see, in this type of project, to model it in 2D would not be realistic. You'd have to take sort of several cuts just along the lengths of the various tunnels. So with a project with geometry that's complex such as this, it's best to model in 3D. So just to create one large 3D model and to just do the analysis that way. The same principle applies to this pile type project here. So this is a pile raft project. As you can see, the geometry is not symmetrical, and it's made of sort of dozens of different piles here. So once again, to model this type of project in 2D wouldn't be practical at all. So this would best be modeled in 3D. So that's another main principle to sort of take from this part of the presentation, is that non-symmetric geometry or complex 3D geometry typically constitutes a 3D analysis. Okay, so let's just sort of summarize what we went over. Okay, first and foremost, symmetric geometry is better suited for 2D modeling. Geometry that is especially long in one dimension can be modeled in 2D as long as the forces acting in that dimension are negligible. So that just goes back to the whole concept of plane strain geometry. And then complex geometry that cannot be realistically simplified in 2D must be modeled in 3D. So we'll get more and more into these types of projects later on into the presentation. But just keep in mind that the more complex your project geometry becomes, the more non-symmetrical it becomes, the more it would warrant a 3D modeling and analysis. Okay, so what we'll do now is we'll have just a quick quiz. It'll be 3 questions long, multiple choice. You'll have a total of 5 minutes. So just take your time and make sure to read each question carefully before you select your answer. And then when you're done, just click the submit button, and we'll receive your quiz from that point on. Okay, so next, Chapter 2, we'll discuss why specifically we use 3D analysis. And we'll go over how it's used in 3 specific project types: foundation projects, tunnel projects, and excavation projects. Okay, so for foundation problems, so as you can see, this is a typical pile raft foundation problem, and it is symmetric. But one of the things to keep in mind is that because of the way the different piles behave and react, the loading, although it may be symmetric, the reactions are not. So even though you could, model this in 2D, there would be certain things that you'd be having to sort of make assumptions on, which could lead to over-conservative designs or calculations. So for example, lateral displacement or longitudinal spacing, that can be accounted for in 2D analysis. So if you were to take a cut along this axis or this axis, although the geometry itself is symmetric, the longitudinal spacing may not be. And also you can't take into account. And also, if you'll remember from our first presentation, our first lecture, there are actually areas of high strain or high stress. So for example, this area here, and here, and here. Certain parts of the soil, because they're receiving stress from multiple piles, they receive more stress than, for example, the soil around this area and this area. So that's another thing that can't be accounted for in 2D analysis. So just keep in mind that with group pile foundations, even though the geometry itself may be symmetric, the conditions are not. So that's why foundation problems, specifically group pile foundations, are typically modeled in 3D to get the most accurate results. And this just goes into what I was talking about previously. So as you can see, even though the piles themselves are symmetric, they each receive sort of different. They all have different resistances and settlements, just depending on their position. So as you can see, these center piles here behave very differently from the piles along the corner. That's because these piles, interact with sort of their neighboring piles more, whereas these corner piles, they have less interaction involved. So just keep that in mind, that although the geometry itself is symmetric, the piles behave very differently depending on their position. And this is something that can't be modeled really accurately in 2 dimensions. So typically 3D models work best for piles, or especially pile rafts. So here we have, a foundation with underground or adjacent structures. Once again, that typically constitutes a 3D analysis, or an irregular shape such as this. So we went over a pile raft foundation such as this in the previous chapter, where the geometry itself was asymmetric and the pile geometry was asymmetric. Sort of complex group pile projects such as this constitute a 3D analysis. And here we have 3 different methods of solving foundation problems. So first there's the PY analysis, which I'm sure you're all familiar with. It's one of the most widely used methods for group pile foundations. So this utilizes spring elements, and it's partially in 3D. So that's what sort of makes this one of the more popular or the most widely used methods, because one, it's very simple and it's very efficient, but at the same time it can also calculate partially 3D elements, or it can take into account certain 3D parts of the project. Whereas with 2D analysis, once again, it uses constitutive models. However, it does typically sort of apply, it does typically generate very over-conservative results. So even though you get results that, pass design codes, they'd be maybe over-designed, or for larger scale projects, they would, it would require, the designs that you would get with 2D analysis would create costs that are, that far exceed, what you'd actually need. So for example, with a 3D analysis, however, you're able to, this too uses constitutive models, but it's also the most realistic, and it's ideal for pile raft foundation projects because those are sort of the larger scale projects. And with 3D analysis, you can get results that are, more realistic, more accurate, and that could also lead to the most effective or cost-effective designs. So that's one of the main sort of benefits of modeling in 3D, is even though it takes a bit longer, it does require, more effort and more time. Ultimately, you would be getting results that are more optimized, and that ultimately could help you to sort of bid more competitively. Okay, and here's some sample tunnel problems. So here's a tunnel with with various stations and connecting galleries. So once again, this type of geometry would best be modeled in 3D. The same with this type of model here. So as you can see, the rock bolts are included. That's what these sort of portions here are, as well as the a station and connecting galleries. So once again, with larger scale complex sort of underground tunnels and subways, 3D analysis is typically used because these are higher end projects that have larger budgets, and that would really sort of, the only really effective or the only realistic way to model these projects would be in 3D. And then here we have a tunnel with complex construction methods. So as you can see, the rock bolts are included. And then also because, as you can see, these sort of segments here are different colors. So essentially this project was done with a construction stage. So they modeled for each stage of the construction. So each segment represents a different stage of that excavation. And then as well as the tunnel lining. So each band represents a different level or a different stage of creating that lining. So for more detailed projects that require like construction stages or step-by-step sequences, 3D analysis is especially useful. And then also, as you can see here, this would be, I think, neighboring structures or ventilation, and just the geometry. Even though it's symmetric, it would best be modeled in 3D just because of the sort of it's an adjacent structure. So you need to account for loading and displacements in the longitudinal direction as well. In this sort of case, typically strains in the longitudinal direction aren't negligible, so you need to model that in 3D. And then same with these tunnel exits. So here you have an adjacent structure type study. But as you can see, these contours are also very detailed in 3D. So once again, an analysis in 3D would typically benefit this type of tunneling project. Okay, so now let's take a look at the comparisons of 2D and 3D finite element analysis with tunnels. So for this this project here, what happened was engineers decided to see if there are any differences between the results of a 2D and a 3D analysis. So to the left here are just sort of the analysis conditions that were used, and then the loads that were applied to the 2D model. So they took the same exact project and they created a 2D and a 3D model, and then they ran the analysis through to see if there would be any significant differences in the results. And here we have the results in the conclusion of the experiment. So to the left here you have the 2D model and the results that were calculated. So as you can see, here are all the, for example, the bending moments. And to the right here are all the bending moments that were calculated in the 3D model. So as you can see, the bending moments of the 2D model were much more conservative than the results that were generated with the 3D model. Sort of the main thing to take from this experiment, or from this experiment, is that in a 3D finite element analysis of tunnels, the values of forces and moments are less than 2D FEA. So that means that 2D finite element analysis is conservative and may be uneconomical depending on the project. So just keep that in mind. With 2D analysis, the results will always be more conservative, and you may end up sort of over-designing for your project. Whereas with 3D analysis, the results are much more optimized and much more accurate. So that's another one of the trade-offs. With 2D modeling, the modeling and the analysis itself is much simpler. It's much faster and more efficient. Whereas with 3D modeling, it takes a bit longer, or it might take even much longer depending on the scope of your project. But you can rest assured, or you can design with more confidence, because with 3D modeling, you're able to take in displacements in the longitudinal direction and strains in the longitudinal direction. Those are taken into account. Therefore, you can get more optimized results or more accurate results. Okay, and then let's talk about some excavation type problems. So here we have an overview, or an overhead view of an excavation problem. And as you can see, there are certain indentations or corners here that can't be taken into account with the 2D model. So if we were to take a cross-section here, you wouldn't really be able to take into account this corner here, or these corners over here. And also, if you're to take a cross-section in this direction, you still wouldn't be able to take those corners into account. So why is that important? So this is important because of something called the corner effect, in which stress concentration is much higher in the corners. So in other words, because of the geometry of the corners themselves, they react to loads much differently. So they tend to sort of take in a much higher concentration of stress, and also the displacement and the yielding is much less in the corners than it is, for example, at the center of this retaining wall here. So that's another thing that'll be overlooked in a 2D analysis. So therefore, you'd be sort of making certain assumptions, and you also assume that the retaining walls at certain points or displace or deform more than they actually do. So with corners, what it actually does is it reduces the displacement in certain areas. and increases the strains. So as you can see, with a 2D analysis, you would have a very sort of oversimplified or over-conservative model, whereas with a 3D analysis, it'd be much more accurate. And then here's some other excavation problems. So for this one on the left here, as you can see, the geometry is asymmetrical. There's a station, there's an adjacent structure. So with this, just by looking at it, you'd say, okay, this would best be modeled in 3D. Whereas with the one on the right here, as you can see, it's symmetric in the longitudinal direction. There are adjacent structures, but the structures themselves are modeled very simply. So for this type of project, you may be able to model it in 2D and still get acceptable results. But with 3D analysis might also be useful for this project as well. So once again, it really goes back on the engineer. So even though geometry itself may be simple and symmetric, sometimes engineers might want particularly conservative designs, so they'll invest the extra time and the extra effort to create a 3D model instead of a 2D model. Okay, and here's another example of 2D versus 3D analysis, this time for an excavation type project. So as you can see, with a 2D model, you're only able to sort of account for the geometry in this plane, whereas with a 3D model, you're able to get the geometry in all three dimensions, so you're able to account for this cornering effect here. So what will happen is because there's a corner here, this corner will receive greater strain, but also it'll reduce the amount of deformation and displacement in this general area. Whereas with the 2D model, you wouldn't be able to account for that, so therefore you'd essentially be over-designing for this model. Because the 2D model can't take into account sort of the different reactions or the different behavior in the longitudinal direction, you'd have calculations that are very conservative, and you'd have a design that might not be as economical as a 3D model. And here are the results of an experiment where a 2D and a 3D model were created for the same excavation project. So if you look at the chart here, we have the the results charted against each other. So as you can see, this graph here using circles represents the 2D analysis, whereas the lines here with the triangles represent the 3D analysis. So as you can see in the 2D analysis, displacement was calculated to be much more than it was calculated to be in the 3D analysis. So once again, that's due to the fact that in the 2D model, it couldn't take into account the cornering effect. So because of that, it calculated the displacement to be much more than it actually would be. So once again, with the 3D analysis, although it would take longer to create this model and a little bit longer to run the analysis, ultimately you would get results that are more accurate and more optimized. Okay, so now just a quick summary of what we went over. So group piles have geometry that typically make it ideal to model in 3D. And also not just the geometry, but also the reactions themselves need to be modeled in 3D in order to gain something more accurate. And then conventional tunnel and excavation projects can be modeled in 2D. However, the results tend to be more conservative than results calculated through 3D modeling. So just keep that in mind. So even though you're saving a lot of time and effort by modeling in 2D, ultimately the results that you get will be more conservative than a 3D model. And then high-end tunnel projects that include connecting gallery stations and asymmetrical geometry are best modeled in 3D. So we'll go into more detail about 3D tunneling projects at the very end of this presentation. I'll go over a case study where 3D analysis was used very effectively for a complex 3D tunnel project such as the ones we just discussed. Okay, so before we continue, we'll have another quiz. It'll be 3 questions once again, multiple choice. You'll have up to 5 minutes to answer all the questions. So once again, just take your time and just read each question carefully, and then when you're done, click Submit, and we'll receive your quiz.
Quiz ahead of time, so I'll just start moving forward now. So now we'll move on to Chapter 3, which is really sort of the bulk of this presentation, is how to specifically utilize 3D analysis. So we'll be going over just the main fundamentals of modeling in 3D. We'll start off with element types, then we'll go into sort of the finer points, or just an introduction actually to meshing, and then modeling material properties, loads, boundary conditions, and then finally how to interpret the results that your 3D model analysis gives you. So first, let's go over the just the process of 3D modeling. So first, obviously, you create your 3D model, then you perform the analysis, then you interpret the results. That's sort of the main sort of portion, or the main process. But within this process of modeling, there's certain things that need to be done. So it's sort of a process within a process. So as far as the modeling process, we start off with creating our geometry, defining our boundaries and our conditions. Then we define our material and structural properties. We generate mesh, we assign loads, and we assign boundary conditions. So as you become more sort of skilled with numerical modeling, this process will become more and more like sort of second nature to you. So let's discuss just the introduction, or let's discuss each of these points just in a little more detail. And just keep in mind sort of this top bar here, this sort of flow chart. So we'll start out with the geometry, and then we'll continue on until we're done modeling our loads. And then after we model our loads, we'll go over analysis and interpreting the results. So first, let's discuss geometry. So there are three main types of elements in numerical modeling programs or software. So first, there's the 1D element, or the line element. It's just two nodes connected by a line. These are typically used for piles, for beams, for trusses, just for for simpler projects or simpler sort of structures that can be sort of simplified into 1D elements. And as you can imagine, the analysis time for these are very simple and very quick. These are typically, usually done by hand, but with numerical modeling comes in handy when you have sort of several of these 1D line elements connected. Next, there are 2D or planar elements. So these are sort of the next sort of level in complexity. As you can see, it's a series of nodes and lines that are connected, but within this sort of frame here, there'll be what's called a surface. And upon this surface, you can model strains, displacements, and moments. So in addition to sort of these edges and these nodes here, the surface can also be analyzed. This is typically used for retaining walls, retaining walls. Let's see what else, as well as excavation types, and other sort of flat structures that you can imagine. Next, there are 3D or solid elements, which are the sort of highest level. So as you can see, it consists of a series of lines and nodes that are all interconnected, but it's done in full 3D. So not just 2 dimensions, but 3 dimensions. So as you can imagine, instead of just having one surface, it has 6 surfaces, including an interior, all of which can be analyzed. So with this, you can model soil elements, you can model any type of sort of structure in 3D, and there's no limitation to what kind of geometry you can create in this. So this is used for, I guess, more complex or more higher end type structures. However, because there's a lot more sort of data that needs to be analyzed when modeling or when analyzing a 3D element, the analysis takes much longer when you use 3D elements. So essentially, whenever you have like larger type projects, you'll be using a combination of these 3 elements. So for example, your soil elements would be modeled in 3D, but if you had piles, you'd model them with 1D elements, and then for your retaining walls and various plate type elements, you'd use 2D plane elements. So later on, I'll show you an example of a project that uses all 3 of these elements. Okay, so here's an example of just a pure sort of 1D element analysis. So this is just a simple truss. So as you can see, just the project geometry itself is very simple, and I believe this is the stress in each member. So you can get the stress, the strain, the axial forces, and the moments if you use these 1D elements here. And now retaining wall. So this is an example of a 2D analysis. So as you can see, when you do a 2D analysis, you use your planar elements, and then also you can get your strains and your stresses, but now it's much more detailed. You can get them along these contours and these surfaces. So instead of just having your results just along one line, you can have it along an entire surface. So this analysis takes a little bit longer to do, but if you have a project such as this, where you have maybe soil elements, as well as some interaction with a retaining wall, then a 2D analysis would be very beneficial to you. And last, a 3D analysis. So this is a 3D slope, and we'll be going over this specific example later. But this is fairly straightforward because of this sort of notch here, this geometry. The engineer opted to model this in 3D. And as you can see, you can only get your results along this plane here, but you can also extrude them along the entire length of the longitudinal direction. So it's really depending on your project geometry and your project type, you'd sort of decide which elements to use. But the main sort of things to take away from this is that each has its own purpose and each has its own shortcomings and weaknesses. The main strength of 3D solids, obviously, is that there's no limitation to what you can model, but the drawback is that the analysis takes longer. There are more variables to take into account. Whereas with 1D elements, the analysis is very simple and very fast, but it's sort of more limited in terms of the geometry that you can model. Okay, now creating 3D solids. So later on when you're doing your own 3D modeling, you'll find that usually what you do is you start off with a 2D profile such as this, and then what you'll do is you'll extrude it into a 3D element. Now there are certain special commands that all numerical modeling programs have that allow you to do this. For example, Plaxis 3D, GeoStudio, as well as Midas GTS all have certain options that allow you to model, that allow you to create 3D solid elements from 2D profiles. The same principle exists, for example, if you want to create a model or any sort of hollow opening, you can have a single line and then you can extrude that line into a 3D solid as well. So later on when we get more into how to do your modeling, we'll discuss these options in detail, but just keep that in mind that all sort of 3D geometry or 3D solids sort of start with 2D geometry. Okay. Now, for example, 3D geometry, as it becomes more complex, it requires sort of more commands in order to create the solids. So, for example, let's take a look at. You'll start off with maybe just like a solid block here, but in order to create these two soil layers with the contours, you'll have to trim the top and you'll have to divide it. You'll have to assign different sort of properties. So this is just to sort of give you an idea of how 3D modeling is done, because once again of its complexities, it has various sort of tools that help you to sort of simplify that process. So as I said, this is just sort of an introduction to it. Later on, we'll be discussing these options in greater detail, and also. I believe in that first lecture that we had 2 weeks ago, I discussed construction stage analysis. So for those of you who are wondering how staged analysis is done in 3D, what happens is, they'll create their 3D geometry, they'll create their tunnel, and what they'll do is they'll take these flat surfaces and they'll model those in 3D, and they'll use it to cut the tunnel in certain sections. As you can see, all the segments are here in different colors, and each of those represents a different stage of the excavation. So that would be how you would model your staged excavation, just through dividing your surface. Okay, and another great sort of advantage of 3D modeling is that you can also you can import topographic data to generate really intricate contours, detailed contours. So for those of you who have, for example, a TGM, the Terrain Geometry Maker, what it does is, I'm sure you're familiar already, but for those of you who don't have this, it's a really great program that allows you to import all the coordinates for your contour graphs, for your project site. And what you can do is you can take those coordinates, import them into a numerical modeling program such as GTS or Plaxis, and you'll be able to get very detailed contours for your 3D model. So this becomes especially useful for projects where you need to take into account different sort of values of soil pressure along the contour. So once again, just keep that in mind. This is actually something, to create a model such as this doesn't seem as hard as it might seem. If you have the TGM or the Terrain Geometry Maker, you can just import those coordinates directly into the program, and within just a matter of seconds, complex geometry or complex or detailed contours are created just automatically for you. Okay, now we'll go into boundaries, or creating the size of your project. So the main sort of rule to keep in mind is that the model must extend far enough away from the zone of interest for the variations in stresses and strains to become negligible. In other words, your model has to be big enough so that the stresses and strains from the point of interest won't be negligible as you go farther and farther away from it. So I guess the best way to illustrate this would just be to sort of show you this picture, or to show you a picture. So for example, here we have a shallow foundation. So here's your foundation, and here is roughly what the size of your model should be. So essentially what this is telling you is that if your foundation is around sort of this width, b divided by 2, then the length of the model itself should extend about 5 times half the width of the shallow foundation. So for example, when you're doing your analysis, there'll be certain strains and displacements occurring in this area, but then as you go further and further away from that area, they become sort of more negligible. So that's what the sort of that previous definition I showed you was talking about. You just need to keep in mind that your project has to be big enough or far away from your project has to be large enough so that sort of your area of interest, the strains and the things that are happening in that area of interest will sort of be dissipated further and further away from it. So for example, once you reach sort of this point of the model, it isn't directly affected by anything that's happening here. Whereas if you were to make your model too small, for example, say you were to end your project geometry over here, then the stresses and the strains would go beyond that area, and there'd be certain things that you weren't sure about. So what I'll do is I'll just show you sort of a series of different sort of guidelines that are available to you when you're creating your foundations. So if say you're doing a deep foundation, it's just good to have like this size of a model. Once again, these aren't really sort of set in stone, as you can see. It's just sort of just roughly around this area. These are very conservative, so you can do them a little smaller if that works for you. But just keep in mind that your boundaries should be far away from enough from your stresses and your strains, so that you have everything modeled and everything included. So what I'll do is I'll give you all a copy just of this PowerPoint at the end of this session, and then also we'll post the recording, so that way when you start doing your own numerical modeling, you'll have these just sort of as a reference. And SPW is just another it's just an acronym for sheet pile walls. So as you can see, these are fairly useful whenever you're creating your project for the first time or your first numerical models. It's good to have these as a reference just so that you can sort of get a ballpark of how big your model should be. And once again, it's all sort of a function of your just your project geometry. So however big your embankment is how big your model should be. And the same principle applies to your tunnel as well. So these are just good to have as a reference so that when you're creating your own models, you'll get an idea of how big your overall model should be. Okay, and then these should be all familiar to you as well, the different types of boundary conditions, fixed, pinned, and sliding, or also known as rollers. And in order to assign these boundary conditions, what you would do is you just select certain nodes along the sides here, and then you'd select your directions of freedom. And we'll go into more detail about this later. But for those of you who are wondering how to assign boundary conditions, this essentially is just how it's done. Okay, so now let's discuss material properties. So we discussed constitutive models, in detail during our first lecture. So with numerical modeling programs, essentially what they'll have is a database of different constitutive models that you can choose from. Now, it's not really important to become familiar with every single one of these. Maybe there's just a couple of them that you need throughout your practice. But just as a review, for example, the Moore-Coulomb, it's essentially used for shear and normal type stresses. This is the most standard and the most basic of the constitutive models. It's usually used for all of your projects. I'm sure all of you are very familiar with it at this point. Then Drucker-Prager is used for plastic yielding, on Mises for ductile materials, Hoek-Brown for rock failures. So if you have like rock excavations or rock foundations, you're going to use a Hoek-Brown constitutive model. Tresca for undrained, as well as drained soil behavior. Modified Cam Clay for consolidation, and then Jardine for nonlinear elastic materials. So it's really just important to become familiar with any type of constitutive model that you're using. And then just later on when you're doing your numerical modeling, you'll just have the option to choose the numerical model that you need. And then once you choose your numerical model, the program will just ask you for certain material properties and structural properties. So I won't go into too much detail about these. These are fairly straightforward. But one thing that I do want to stress and point out is that it's always very important to check your units. So for example, here it's in tons and meters squared. So a really easy mistake to make is when you're starting off is just to see, you have your chart of values and to just enter them here automatically without checking the units. So just make sure that your units of your data and the units of the numerical modeling program line up. Otherwise, as I'm sure you can imagine, your results aren't going to make any sense. So that's just the key thing. Just always make sure your units line up. And then as far as like seepage, you'll have these parameters, your permeability coefficients, unsaturated properties, and then for consolidation type projects, you'd have these sort of variables to take into account. So I won't go into too much detail. Once we go into sort of each sort of separate section later on in the course, we'll discuss these material properties in greater detail. But just keep in mind that it's really important to have your materials properties ready so that you'll be able to enter them into the program when the time comes. Okay, so now let's talk about meshing. So just some general guidelines just about meshing. So first and foremost, it's just important to use the simplest type of finite element that will do the job. So for example, if you have just a really small, sort of straightforward project, just use, a really simple mesh set. There's no sort of reason to make it more complex than it has to be. And then also, another important thing to remember is don't use complex or special elements unless you're absolutely sure that you need them, and two, that you fully understand how to use them. So I believe in the first course, I introduced you to interface elements, which are used for soil structure interaction. There are also, several other different sort of special elements that are used to do sort of more complex or higher end type projects, and we'll discuss those type of elements in detail later on. They're extremely useful. They're used, they're rolled over by various engineers. But it's just a matter of understanding them before you use them. So sort of one of the purposes of this course is to get you guys sort of acclimated to special elements and sort of special options that are available to you in numerical modeling programs that aren't available in any other sort of type of analysis process. And we'll be discussing these, once again in greater detail. We'll sort of show you how these sort of special elements can be used to help you get better results. But in the meantime, right now we're just sticking to the basics. So just keep in mind to don't use any complex or special elements until you've received some training on them or until you studied them up first. Okay, and then use the coarsest mesh you think will capture the dominant physical behavior of the physical system, particularly in design applications. So for those of you who are new to mesh, coarse mesh is just another way to say larger mesh, and fine mesh is just another way to say smaller, more refined mesh. The reason that, so for example, in this image here, as you can see, as the mesh gets closer to the opening, the mesh becomes finer. So why is that? The reason that the mesh becomes smaller around the opening is because the stresses, the strains, the displacements, the moments, etc., become stronger or more prevalent in this area. So along areas where you have large amounts of strain, or maybe certain areas where you're expecting failure, it's really important to have a more detailed analysis. So the finer your mesh is, the more detailed your analysis will become. Whereas the coarser your mesh is, the larger it is, the less detailed your analysis will become. So as you can imagine, maybe certain along the edges of this sort of mesh set here, or the edges of this model, the displacements and the strains aren't really of interest to you. You sort of have a better idea of what they'll be. Whereas along the lining of the tunnel and along the opening, that's really the area of interest. That's really the area that's of most interest to you. That's where all the changes, the failures, etc. are happening. So you want the mesh to be finer there, because the more finite elements you have, the more results you'll get, and you'll always want more results for these areas over here. Okay, so some other things to keep in mind. So initial finite element models often must be substantially revised to accommodate design changes. So for example, when you're creating your first model for your project, it's always a good rule of thumb to keep it simple. Because I'm sure you're all familiar with this process later on as a project develops, as you get more information. Maybe there are certain things that need to be changed, need to be added. In this case, your model will be changing as you draw sort of closer to your deadline. So it's always a good rule of thumb to keep your model simple at the beginning, and then later on, as you receive more information about the project, to make it more detailed. So that's another important thing to keep in mind. So if you create a really sort of complex model at the beginning, it's not really an efficient way to do it, because in all likelihood you'll have to change it later on. So yeah, just keep that in mind. Just keep your model simple at the beginning, and then later on you'll be able to refine it over time as it draws to its conclusion. Okay, and then just once again, just going over mesh refinement. So fine meshing is done in regions where you expect a high gradient of stresses, strains, and displacements, etc. So here's some other examples of regions where you'd want fine meshing. So for example, along cutouts, any sort of openings, along cracks, or areas where you'd expect cracking, you want your meshing to be finer. Also, entrant corners, you'd need fine mesh. Concentrated points, so if you have any point or distributed loads, any sort of areas that experience any type of loading, you'd want the mesh to be finer. And then if you have any sort of welds, so for example, much strain is placed on these welds here, that's where cracking would occur, so the mesh would be finer in those areas. Abrupt thickness changes, material interfaces, so say if you have Any sort of changes in, for example, soil strata, you'd want the mesh to be a little bit finer, or soil structure interaction, you'd also want the mesh to be finer there as well. Okay, and here's just some more examples of mesh refinement. So as you can see, along these corners here, the mesh is, or along these openings, excuse me, the mesh is much finer because that's where you could reasonably expect the cracking to occur and failure to occur. Whereas in the center here, not much happens, so the meshing is much coarser. So this is just all done in efficiency, so that your analysis doesn't run longer than it needs to. And then also along certain points here where the we'd expect failure or cracking to occur, certain openings, entrant corners, etc., the mesh becomes finer. Okay, and now let's talk about just the aspect ratios, or the shapes of your meshing. So it's always a good rule of thumb to aim for a 1-to-1 ratio when it comes to your meshing, whereas sort of longer, skinnier shapes, anything up to a 10-to-1 ratio are not ideal. The reason that these aren't ideal is because sort of the longer that your mesh shapes become, the less reliable your results will be. So essentially, if you create a model with really long meshing, it doesn't necessarily mean that your results won't be accurate, but there's a higher chance for sort of errors. So in order to avoid that chance for error, just try to create meshing with a 1-to-1 ratio that's sort of smaller, more compact. Any sort of long, sort of skinny elements, that's something to look out for. And then later on, we'll discuss how to create your meshing and how to sort of make your meshing sizing according to your needs. But it's always good to have that principle in mind before you start learning how to mesh. Okay, and then another rule of thumb is that elements must not cross physical interfaces. So for example, if you have two different materials, for example, say you have, I don't know, steel on this side and concrete on this side, you want each material property to have its own separate mesh set. You never want to have a mesh have any to share material types. So for example, here would be something negative or a bad example. Whereas here, you'd want a physical interface. Usually, there'd be an interface element here. We'll, discuss that in detail later. But then your mesh sets on each side would be sort of separate, and they'd be connected by these nodes. So it's really through the nodes and the interface elements that the program that you'll be able to sort of calculate the interaction between different soil layers or different structure types. Whereas if your mesh sets sort of cross here like this, that could lead to a lot of errors, a lot of miscalculations. So that's just another thing to keep in mind. Whenever you have a change in physical interface, make sure first off that there's nodal connectivity, that there's a series of nodes connecting your elements, or they're connecting your mesh elements. And then also make sure that you don't have any elements that cross over like this. Okay, and then also preferred shapes for FE modeling. So the general rule of thumb is that you'd want quadrilateral elements are preferred in most cases. That's just speaking generally. So the reason quadrilateral elements are preferred is because it's easier to get the 1-to-1 ratio. If you look to the left here, as you can see, all of the elements are relatively within the 1-to-1 ratio. Whereas if you have triangular elements, you can have elements that'll be a little bit longer, that'll reach the 10-to-1 ratio, which typically you'd want to avoid. But triangular elements do have special purposes. For example, areas of transitions, of corners, it's a lot easier to do meshing in those areas with triangular mesh. So later on, as you become more experienced with meshing and finite element analysis in general, you'll sort of be able to understand when it's best to use each. But when you're starting out, it's always just a good rule of thumb to just stick to quadrilateral elements, just because it's easier to get the aspect ratio that you desire. Okay, and now let's talk about the last section, or the last sort of portion, which is applying your loads. So later on, when you're using your numerical modeling programs, you'll find that there are different sort of input options that you use to input your different loads. For example, self-weight, you would just bring up this input menu, and you'd put your, the program would just sort of sense which direction your self-weight's in. You just have to input that, and the program will take care of the rest. Same with defining nodal loads and beam loads. So for example, if you have a point load, you just select a node on which to apply that nodal load. You'd select the force, and then you just choose to apply it. And then with beam loads, if you had a distributed load, or if you wanted to put moments, etc., you'd select a line, or a length, or a curve, and then you'd apply that distributed load upon it just through an input menu such as this. So once again, we'll go into greater detail about how to sort of use or to incorporate these input menus when you start doing actual models. And then same with pressure loads. So for those of you who are wondering how we're able to sort of model 3D loads. You can model a distributed load such as this by selecting a certain face, and then the program will just sort of automatically select the nodes and apply the forces along a distributed plane. And say, for example, if you had maybe more complex loading type with maybe a higher sort of level of loading in this area as opposed to this area, there are certain things you can do to manipulate the program to produce that sort of asymmetrical loading. And then also another great sort of advantage of numerical modeling is that you can, in addition to sort of just normal distributed and point loads, you can also model more complex loads such as temperature load. So for example, if you have maybe a project in a region where temperature loading might be something of interest to you, something that you want to account for, what you could do is you could select this temperature load option. You can input an initial temperature and a final temperature to account for your differential, the differential in maybe, for example, summer to a winter season, something like that. And you want to see how that, affects the structural integrity of your structure or your building. You could input this temperature load, and the program would, account for expansion, account for strains, etc. You can do all of this just using this sort of option. And the same with a pre-stressed load. So, for example, if you have maybe something like maybe a beam or a bridge with some pre-stressed tendons, you could simulate that pre-stressed load on those tendons just using an option such as this. So as I mentioned earlier, we'll go into more sort of detail about these special options later on, but I just wanted to sort of let you guys know the options that are available to you. So this is another sort of unique strength of numerical modeling, is that you can do, you can take more variables into account, and for variables such as this, a numerical modeling program or numerical modeling approach would really yield good results for you. Okay. And last, let's talk about how to interpret your results. So here's the project that I mentioned at the beginning that I was going to sort of use as an example. So this is a conventional stage excavation project with a pile raft foundation as well as a retaining wall. So as you can see in this project, I used all three types of elements. So to the left here, this is just the finished project with all the meshing, and this is another view of the project just with a transparent view so that you could see the retaining wall as well as the piles. But the soil elements themselves were done in 3D with solids. But then later on, as you can see, the retaining wall was done with 2D planar elements, and then the piles themselves were done with 1D elements. So as you can see, each element type has its own, sort of use, but it's usually best or most efficient when you have a larger scale project to use a combination of all three. Okay, so here's just an example of what the results look like for this particular project. Generally, with most finite element programs, maximum values are typically done in red. So this is these are the results for displacement in the dxyz plane. And as you can see, along the center of the excavation is where the maximum displacement occurs. And as you go further and further away from the excavation site, the displacement becomes less, up to the point where it's almost sort of negligible. And that's what I was sort of talking about with boundary conditions. So for example, if I were to make my model too small, if I were to do the edge along here, then there'd be strain going past that point that I would want to account for, and I want to make my model bigger. So as you can see, the model is fairly big enough, so all of everything, all the strains and displacements are within that range. So as you can see, if you look to the right here, all numerical modeling programs will include a legend to help you interpret your results. So for example, along sort of this red area here, the range would be this displacement, and the units are in meters, whereas in the darker blue areas, there wouldn't be any displacement at all. It'd be around this range. So that's just so at a glance, you can sort of get an understanding of what your displacement would be. And then deformation. So with this option, I was able to sort of exaggerate the deformations. So as you can see here, I have my deformation, and then the scale factor is 3 times. So this is 3 times what the deformation would actually be. But the reason I exaggerated it was just to get a better understanding, or to get a sort of an easier view of where my deformations would occur. So for example, when I'm doing my design, or when I'm sort of designing my retaining wall or something like that, here I would understand that this is where my greatest deformation would occur, and here's, there might be certain things I want to do to minimize the deformation. So that's another option that's available to you, is with the deformations, you can exaggerate them to get a really sort of clear or a better understanding of where those deformations would take place. Okay, and then here are the results for my retaining wall. So as you can see, what you can do with your model is you can isolate certain parts. So later on, if you just want to see your retaining wall, you can just turn those elements on and focus purely on just the results of your retaining wall. And then reading the results is a similar process. So the maximum results are typically in red. You'd use your legend to sort of reference what those results are. So this would be the element forces. So as you can see, everything is clearly listed in the post-processing section. So you have results in 1D for your 1D elements, for your piles, results in 2D for your planar elements, and then later 3D elements for your soil elements. In numerical modeling, all of your results, you get this sort of large sort of plethora of results, and it really is up to you to sort of figure out which ones that you need for your final report. But everything is, clearly organized. At least, this is a Midas GTS example, so all of your results are organized in this sort of menu, so that you can, open these, you can reduce these to find the results that you specifically need. Okay, and here's some examples of 1D elements for the piles that I was discussing. So these are all in 1D, but with 1D elements you can get your moments as well as your forces, and it's just following the same sort of process. You'd use this graph for this legend here to determine maybe your maximum or your minimum ranges, certain maybe moment ranges that would be of interest to you. You could just find those just by reading this graph. So one of the advantages of numerical modeling programs is that although 1D analysis is fairly simple to do by hand, if you have large sets of 1D analysis, for example, a large group pile configuration such as this, with a numerical modeling program, you can create the model fairly quickly, and the analysis can be done in like a matter of minutes, and then you have all of your results ready for you in a very convenient graphical format. So something that would take you maybe a couple of hours to do by hand or through a spreadsheet could actually be reduced to maybe just a couple of minutes using a numerical modeling program, and the results look better. So those are certain advantages to using numerical modeling programs over maybe other practices that are out there. Okay, and then for those of you who maybe want to import your results to a spreadsheet, so with Midas GTS, this is a very sort of specific example to GTS, but I'm sure Plaxis and GeoStudio have their own ways of doing it as well. So if, for example, say I have my retaining wall, but I want a spreadsheet that I can use to give to a client just for some more clarity, what I can do is I can tag certain ranges or certain sections, and then I can export those results into a spreadsheet. So as you can see, it gives the X, Y, Z coordinates, so I know exactly where that result is, and then it gives the value. So I believe this was either displacement or strain, I can't remember, but these are the results for that. And then also, by selecting maximum and minimum, the program automatically just sort of tags where those maximum and minimum values are. So we'll discuss sort of these result extraction features in greater detail. But another thing to sort of keep in mind is that because the results that you get through finite element analysis are so detailed and so in-depth, there have been several sort of tools that are available to you to help you filter those results. So that was one of the main holdups of finite element analysis when it first came out. Is engineers said, okay, great, we get all these results, all these spreadsheets, but what does it mean, and how do I sort of filter this out to what the client needs? So because of certain developments that have sort of come forth in the finite element analysis industry, it's becoming easier and easier and simpler to isolate the results that you need. And these are, what I just showed you is just a couple of examples of how to get those results. Okay. So let's summarize what we learned. So first, the three main finite element types are lines, 1D elements, planar elements, which are 2D, and solid elements, which are 3D. And then later on, as you start creating your numerical models, you become more familiar with these types of elements and how to use them sort of interactively. Okay, then boundaries should be just large enough to cover the area of interest without being unnecessarily large so as to lengthen analysis times. So just keep that in mind, that the larger your project model is, the longer your analysis will take. But you also want to make sure that your model is still sort of large enough to cover all of your necessary boundaries, so that all of your strains and displacements, all of your results are within that range, or within the size of your project. And it's really, just to start off, it's good to use the examples that I showed you just as a reference. Okay, so mesh sets should be made as simply as possible, with finer mesh being generated around areas of high strain. So just keep that in mind, that fine mesh refers to smaller mesh, and that smaller mesh needs to be generated around areas where you'll see strain or failure, or areas that are of particular interest to you. And then coarse mesh is the opposite. Coarse mesh is large mesh, and that should be generated around areas that are usually around the edges of your boundaries, parts that aren't of a particular interest to you, but still must be included in the model. Okay. Then material properties, loads, and boundary conditions are intuitively generated through the use of input menus, and the user must input all properties carefully. So in practice, it's very simple. Just open the input menu, import your results, or input your data. But just remember to import these properties carefully, that you have everything lined up. Usually, sometimes, the mistakes that cause the most hassle are the simplest mistakes. There have been many times when, even in my own experience, where I forgot to check the units, or I sort of misread the spreadsheet, and I inputted my results, I inputted my properties incorrectly. So just make sure to not take the step for granted, to just do it slowly, and just to make sure that you understand what you're inputting. Okay, and then FEA results are organized in a post-processing section that can filter and display graphical results on models with contour bands. So, as you become more experienced with finite element modeling, you'll be able to sort of see how these contour bands can be used to your benefits. So, for example, instead of having to go through this large spreadsheet of numbers and finding, your range, you'll be able to do it very intuitively just using the contour graphs. And then later on, if you want to create your spreadsheet, you can just use certain filtering options to export your results. So ultimately, with finite element analysis, you get a wider range of results, more detailed results, but you also have certain tools that are available to you to help you extract the results that you need, so that, for your final report, you won't just have this, big stack of papers. You'll have something very fine and condensed and specific to the client's needs. Okay, and I believe that's it for the summary. So before we go to the Chapter 4, which will be going over the case studies, we have one more quiz. Once again, it's multiple choice, and you'll have up to 5 minutes to complete it. So, just take your time and read each question carefully. Section, which will be going over just a couple of case studies. So for this case study, or for this section, I included one high-end project, but I also included 2 conventional type projects that were modeled in 3D, just because I sort of mentioned previously that you don't necessarily need to have a very high-end complex project for 3D analysis to be useful, and I'll be going into more detail about this after we go over this project. So for our high-end project, I selected the Inje tunnel in South Korea. So for this project, it consisted of 2 adjacent tunnels that were built sort of along this curve, as you can see. But in addition to these 2 tunnels being built adjacently with connecting galleries, there are also 2 connecting galleries here on these 2 levels here, where vertical shafts were needed for safety reasons, and I'll get more into detail into that later. But also keep in mind that it was built along, the tunnel exits were built along slopes, so also, as you can imagine, a slope stability analysis needed to be done, adjacent structure analysis needed to be done. So there's 7 different analysis types that needed to be incorporated into this, very complex structure. In addition to that, a maintenance building was built at the end of the tunnel. And as you can imagine, another adjacent structure analysis needed to be done, a foundation design needed to be done, as well as a slope stability analysis for this portion here. So this is all done using a 3D numerical modeling program, or midas GTS to be specific. And let's take a look here. So the reason that these connecting galleries were included was to include safety and ventilation systems. So for example, this is a rather long tunnel. So in order for an adequate fire safety system to be installed, what they did was they included sort of a storage section here for all the water. So in the event of a fire, there'd be enough water to supply the sprinkler system. Also, there were shafts special lanes for maintenance vehicles. In the case of an emergency, a maintenance vehicle would be able to come very quickly. I won't go into too much detail about the different sort of supply routes, but as you can see, this was something that was taken into account for the design. So as you can imagine, with a project of this sort of size and scope, sort of absolutely needed a 3D modeling tool. So midas GTS was used. Ultimately, was very successful. And they were able to take into account every sort of variable to keep in mind. So in addition to the analysis types that I mentioned, there was also a seepage analysis. So the tunnel itself was built about 132 meters beneath a creek, and depending on the season, the water level of that creek would sort of rise and fall. So because of this sort of additional layer of complexity, a seepage analysis needed to be done to take into account the effects of sort of water pressure on the tunnel. So as you can imagine, as the creek filled up, the water pressure increased, and then a greater level of water pressure was exerted on the tunnel itself. So in order to account for that, the seepage analysis was done, and they were able to analyze the effects of the pore water pressure on the tunnel structure, and they were able to design the tunnel lining and as well as the reinforcements accordingly. As you can see, the contour graphs were especially useful to help them understand how the surface water or how the water behaved, how the flow behaved, and how the strain increased as the water level increased. Okay. And then just for the tunnel junction design itself, as you can see, there are several sort of connecting galleries along the length of the tunnel. And these were done just with 3D modeling. As you can imagine, it was rather extensive. A whole team of engineers was working together on this. Each was given a different section. But just through the use of 3D modeling programs, they're able to take a very sort of complex, high-end project and divide it into several sections to simplify the process. And then, later on, as the project sort of neared its completion, everybody was working together to bring their pieces together. And just through using numerical modeling as a tool, they were able to obtain, very good results, and the project ultimately was a success. Okay. So now let's talk about just those conventional projects. So I'm sure many of you would like to work on maybe a higher end project such as that, but for the most part, everyday work consists of conventional smaller scale projects. So I didn't want to give you the impression that 3D analysis is only used for those types of projects. It's actually used quite regularly for conventional projects as well, specifically because you can obtain more optimized results. So for example, this is, I showed this in a previous sort of slide, but this is a conventional sort of 3D slope stability analysis, and one of the reasons this was done in 3D was because of this sort of notch here. In order to account for this notch, it wouldn't really be as effective to do it in 2D, so they chose to do it in 3D. As you can see, the meshing is triangular, but the 1-to-1 ratio is maintained, so it's okay. And then here is just some examples of the results. So a model such as this would actually only take maybe an hour or two to create, just to create the model itself. As far as doing design alterations, that's another story. But creating the model itself in 3D isn't that much of an issue, especially when the geometry is simple. And then as far as your results, the displacement is included, element strains and stresses for your soil is included, factor of safety is calculated automatically for you. And then just using the this legend here, you can sort of get a grasp of certain ranges or certain depths of where displacement would occur. So it would be the maximum here in this red range, and then it would sort of taper off to 0 here at the bottom. Okay, another example of conventional analysis would be the seepage type project. So this was a seepage project with construction stages. So essentially, for this project, they were going to install a wall as well as to cut away this portion here. And because this sort of side of the project, I believe this was an embankment or some kind of water, body of water was located over here, there's going to be seepage from, this area of high pressure to this area of low pressure. So they just wanted to sort of calculate or to predict how the water would flow and to decide once the excavation was complete. So as you can see, since this is a construction stage analysis, there are different sort of stages. If you look to the left here to the drop-down menu, you can see different stages. So step 2, step 3. I believe these are different time periods that the engineer decided to include, just so that he could have something more detailed and that he could predict, for each time period, how the model would change. But as you can see, the results themselves are very detailed. Even though this project, it probably only took maybe an hour or so, I believe, to model. The results themselves are very detailed, so that you can have everything from your flow rates, your total head, your pressure head, your pore pressures, etc. So as the engineer was, able to get these results, he was able to filter them to sort of show the client specifically, what they needed. And in the meantime, he had this wealth of results that, any type of question that came up, he had something there. So any type of variable that came up, it was already accounted for through this program. So as you can see, eventually, as you go down the stages, so now we're in stage 3, so now this is being cut away. So here he calculated the total head. So as I mentioned before, there's a body of water on this side of the embankment or the body, and then since the water pressure is high over here, this area here is red, so there's a high water pressure, but as you go to the left here, it lessens. So as you can imagine, the water flowed from the right to the left. And right along this region here is probably the region of most interest because that's where the water would be seeping out from. And that's where you'd sort of need to, design your wall to sort of maintain or to account for that pressure. And then here's like the final stage. So this is stage 5, the last stage of the construction. So this has all been excavated away now. And now the engineer wanted to see the flow rate. So as you can see, this area in red here is of most interest because this is where the sort of the main bulk of the water will escape through. And the program, itself is very sort of flexible. It can also take a 2D sort of flow path, and it can show you just graphically what direction the water is flowing towards, and also maximum areas of flow. So as you can see, this area in red here is, obviously part of most interest. This is the engineer would obviously have to design the wall to withstand that sort of pressure. But just using, this model could have been done in 2D, but the engineer chose to do it in 3D specifically because I believe he wanted, more accurate results. And since it wasn't much of a stretch to do it in 3D, he chose to do it in 3D, and just with a couple of extra steps, he was able to get results that were very detailed and very reliable. So yeah, that's just another sort of main thing that I want you guys to take away from this presentation, is that all types of project types can be done in 3D, even smaller scale conventional type projects. So that's something that we're looking forward to teaching you in the future, is how specifically 3D analysis can be used for smaller scale conventional projects to yield better results, and ultimately to help you cut down on project costs and to be more competitive in your bidding. Ultimately, as technology advances, we found that more and more engineers are using numerical modeling as well as 3D analysis to do their projects. So that's something that we're looking forward to helping you guys out with, is how to incorporate 3D analysis and numerical modeling into your work processes, because it's a very powerful tool that can really help you out in the long run with your work. Okay, so this concludes session 3 of the Midas Elite Center Continuing Education course. Next week's session will be on the same day as well as the same time, so it'll be the 11th. That's a Wednesday at 3 p.m. Eastern Standard Time, and the topic will be soil structure interaction analysis for short excavations. I believe my colleague Arun will be hosting that session. But if you guys have any questions, feel free to contact me either by mail or by phone. Here's my phone number as well as my email address. And once again, we're approved by the Continuing Education Board for the American by AIA, so you'll all be receiving PDHs for attending these courses. And thank you again for your time and your attention. If you have any questions, do not hesitate to contact me. Just send me an email directly, and I'll get back to you as soon as I read it. But in the meantime, thank you again for taking the time to meet, and we look forward to seeing you all next week. You all have a good day now.